Hi, I am Ali Syed, Master of Science in Mechanical Engineering. Now I am going to give a brief description about the rocket propelling nozzle, the nozzle which we use in the aeroplane, jet engines and the rockets. Before starting with it, we'll just discuss about what is the function of the nozzle in an aeroplane jet. What is its function? The nozzle is used to get the thrust in the aeroplane. The nozzle is used, what actually does is the heat and the pressure what you find in the exhaust gases at the end of the engine, it will change the thermal energy into a kinetic energy, and all exhaust gases will be exit with a certain velocity outside the nozzle, which will directly make induced to get a thrust in the aeroplane. This actually the nozzle, the exhaust gas towards the thrust works on the basic principle of the Newton's third law, that every action has an equal and opposite reaction. So we'll just see in further we'll see what are the types of the nozzles and how it's differentiated, classified, and what are the main attributes we require to design that, and further details about the nozzle. Before that, we'll see what are the main and basic nozzles what the aerospace industries use. The first one is the convergent and the convergent divergent. Convergent is a nozzle which we use if the pressure ratio is less than 4. It means the pressure what you are getting at outside the nozzle with respect to the pressure around the nozzle, which is the ambient pressure. If that ratio is less than 4, then you go for the convergent. Usually all the sonic and the subsonic jet planes or aeroplanes what we see, they use the convergent nozzle. Whereas the convergent and divergent nozzle is used in the supersonic and the rocket propeller system. Here what happens is when the exhaust gases come at the throat, the velocity increases, the pressure goes down and the temperature goes down, but further the divergent is used so that the expansion can be diverted. Here as the convergent, here in the convergent nozzle, the expansion is huge. There is no actually a path for the expansion to follow. So the whole velocity, the volume, everything will get zero. Whereas in divergent, as you are getting a divergent shaped nozzle over here, the expansion, there will be a shape for an expansion which will give a further more thrust for the rockets and the jet plane, the supersonic jets. So that is the reason actually why the convergent and the divergent is used. Further we'll see how we are classifying the nozzles in the aerospace industry. First we will discuss with respect to the speed of the sound. First we'll see what is the requirement of the aeroplane. The aeroplane what we are going to design is a sonic or subsonic or it is a supersonic. We need to decide first what is the actual speed we require. We calculate if it is a supersonic or sonic by using the Mach numbers. Mach number is nothing but it's the ratio of actual speed the aeroplane or the jet plane is going to achieve with respect to the speed of the sound. If the Mach number is less than 1, if the ratio to the speed of the aeroplane to the ratio of the speed of the sound is less than 1, then that plane is a subsonic. So with respect to the subsonic, you will decide the type of the nozzle. So sonic if the Mach number is equal to 1, and supersonic if the Mach number is greater than 1 with respect to the 1.4 or 4. So now we'll see what is the changes you will have in the nozzle with respect to the subsonic, sonic and supersonic. If you want to achieve the more speed, which is the supersonic, if you want to have the Mach number of 4, it means the speed at which the plane is going is much more like much more than 1.4 with respect to the speed of sound. Then what you need to do is the type of nozzle will decide what is the actual thrust you are getting. The velocity of the exhaust gases should be more. With respect to that, you will decide the diameter of the nozzle. So with respect to the speed of the sound, this is what the nozzles will be classified. And then we'll see with respect to the geometry of the nozzle. Geometry is nothing but how the nozzle is performing. There are two types of nozzle with respect to the geometry. One is fixed nozzle, other is a variable nozzle. Fixed nozzle is nothing but a nozzle which is fixed with respect to its design. It cannot be changed at any position. Whereas the variable nozzles, the nozzle can vary its diameter. The nozzle can change into convergent and to convergent into divergent. So this more complex variable nozzles are used in rockets and the jet engines. We'll see about the fixed and the variables in further in the types of the nozzles. And other one is the design, as I earlier explained before, the convergent, divergent and the divergent. These are the types of the nozzles what actually we use in the rockets with respect to the design. Now we'll see what are the types of the nozzles. These are actually the 4 major main types of the nozzles what aerospace industry is using at the moment. First one is the ejector nozzle. To discuss with ejector nozzle is a nozzle which will can have the both properties of the convergent and also convergent into divergent with respect to its requirement. If the convergent and divergent is required for the more thrust, whereas in the ejector what happens is the petals of the nozzle are spring loaded and they can be moved. They can be, the whole nozzles, both convergent and divergent nozzles can be dilated to form a convergent and divergent form. So these ejector nozzles are come into consideration when an afterburn operation occurs in the aeroplane. Why is the afterburn operation comes into consideration? Especially this afterburn operations in the supersonic and the rocket engines actually, because you need more lift to go into the orbit actually. So what happens in the rocket is they try to increase as much thrust as possible. So some more fuel is consumed and that has been burned, and the airflow which is coming because of that will be used to get the more thrust. But that afterburn operation will not start unless and until a proper lift for the rocket or the aeroplane has been given. So for that reason what happens is initially the nozzle will be at a certain diameter where the expansion is more, the back pressure into the engine is less, and which will help to make the engine to start at a with low energy actually, with low power. If the back pressure is more, there is more energy is required for engine to run in the aeroplane, in the jet engine. So in the ejector nozzle will help to vary its diameter of the nozzle actually. So first it will maintain one diameter where the expansion is more, it will require less energy for engine to start, and once it achieves the speed, so diameter will be the same diameter, and again the diameter will vary for the actual exhaust gases of the engine. So slowly when it goes to a certain speed, when the speed level of the aeroplane increases to a certain limit where it requires some more thrust to go into the orbit or to go into its path, the whole nozzle the two nozzles in that plane will get dilated and it will form a convergent and a divergent, and then a afterburn operation will start, which I already explained. It's a burning of some more fuel consumption and then making the exhaust gases flow. So when afterburn processes start, there is a more mass of the actual exhaust gases coming in the nozzle. It means it requires more area. So the pressure, the petals of the nozzle will increase the diameter. They are spring loaded. With respect to the mass, with respect to the pressure, with respect to the velocity, the whole exhaust gases coming out of the engine will increase the diameter. So that is the ejector nozzle. It is commonly used in F3 and then CSR71. And then second one is the iris nozzle. It is nothing but an intelligent rotational I-space nozzle. This is nothing but a nozzle where the petals are hydraulically loaded. Whereas in the ejector we see it is a spring loaded. Here they are hydraulically loaded. And even this is also a variable nozzle where you can change where you can vary the diameter of the nozzle with respect to the requirement afterburn process and that. And the rocket nozzle. The rocket nozzle is nothing but a simple convergent and divergent. This is a fixed nozzle because for the variable nozzles, the whole complex, the whole system around the nozzle to change its diameter and to increase the diameter with respect to the requirement is very complicated. It's not easy actually to maintain in the temperature. So as in the rocket system, what happens is like in actual rockets, they use a simple convergent and divergent nozzle because they have the limitations for the weight, they have the limitations for the design, and they have the limitations for the whole area where the nozzle has to be fixed. So for that reason, they will go for simple convergent and divergent. And then another one, we have the low ratio nozzle. This is generally used in the turbojet engines, what we use in the small aeroplanes or the small Boeing aeroplanes and the turbofan engines. Here, the pressure what you're getting outside the nozzle will be less than or will be equal to the pressure in the ambient, which we'll discuss later on with that. So this is a type of the nozzles. So actually what we see over here is the type of the nozzle, the classification of the nozzle, the whole everything has to be decided with respect to the requirement of the speed of the aeroplane. What exactly the speed you need, in what much time the aeroplane or a jet or a rocket has to reach its target. So based on all these things, we have to calculate certain attributes to design the nozzle. Now we'll see what is the main attributes for a design of the nozzle. Before going with it, I just want to give a brief description how the design of the nozzle will affect the thrust, how design of the nozzle will increase the efficiency, fuel efficiency. Here you see, this is the design, this is the nozzle which you see in the black color, and the blue lines what you see is the exhaust gases which is going out of the nozzle. As you see, as they are going out of the way from the nozzle, it is under expansion. It means the pressure which you are getting outside the nozzle is much more higher to the ambient pressure, which is under pressure, which will, because of which there won't be much thrust actually, because of which the efficiency will decreases. The other one is the optimum. This is the main actually the target what all the nozzle design engineers use to maintain the higher efficiency, to maintain the high efficiency, which is they try to maintain the pressure or at the end of the nozzle should be equal to the ambient pressure. If the pressure at the end of the nozzle is equal to the ambient pressure, then the path of the exhaust gases will be exactly the way it is coming out of the nozzle. If there is a pressure at the tip of the nozzle, at the end of the nozzle, that will divert the exhaust gases. Or else, if the pressure, ambient pressure is higher and the pressure what you are getting at the exhaust gases is less, then this is what happens, that is over expansion. Even over expansion, because of which the actual path the exhaust gases has to follow to get the thrust will change, because of which this is what you get the narrow path of the exhaust gases, that is over expansion. So this is the main actually the expansion typical nozzles what you actually design based on, under expansion, optimum and over expansion. This is what actually everyone need. This is optimum nozzle. So this the things. Now we'll see what is the main attributes we require for design of the nozzle. It's all much about what I discussed earlier. First one, what we need is a throat diameter. Throat diameter is nothing but for a convergent, the line what you see over here at the end is a throat diameter. And even for convergent and divergent, in the center what you see the place where the whole diameter goes less, that is a throat diameter. So to decide the throat diameter, we just have to see what is the actual flow area. We have to see what is the actual flow coming out of the engine, actual mass flow of the gases which is coming out of the engine. To calculate that actual flow area, we need to calculate the discharge coefficient. Discharge coefficient is nothing but the ratio of mass. Discharge coefficient is nothing but the actual mass at the end of the exhaust gases at the end of the engine to the ideal mass of the exhaust gases. The ideal is nothing but the exhaust gases that has been calculated at the standard conditions, at ideal conditions of the temperature, ideal conditions of the atmospheric pressure, with respect to the actual mass flow of the all the exhaust gases which are coming at the end of the nozzle. So once you get the discharge coefficient, it will be easy for you to calculate the actual flow area. So once you get that, you will see what is the area required for that exhaust gases to go out with respect to the second, or with respect to the minute, or with respect to the hour. So you can calculate the actual flow area. Once you got the actual flow area, you will calculate the exit area of the nozzle. Exit area of the nozzle is also about deciding the area with respect to the mass flow rate. So whatever mass flow of the exhaust gases you are getting at the nozzle, that has to be exerted, that has to be set. With respect to that, with respect to the speed and velocity, whatever you require, you decide the diameter. If the diameter is less, the mass will take much time to exhaust. If the diameter is more, it will take more time. So it has to be an optimum diameter. It has to be a perfect diameter with which they can actually gain the more efficiency. So which you can calculate using the discharge coefficient. So once you get that, you need to calculate the velocity coefficient. Velocity coefficient is nothing but the ratio of the actual exit velocity of the exhaust gases at the exit of the nozzle with respect to the ideal velocity at the nozzle. So to calculate that, first we need to calculate the Mach number. Mach number, which I already explained earlier, it's the speed of the aeroplane with respect to the speed of the sound. So we need to calculate the Mach number, and then we need to calculate the pressure ratio. Pressure ratio is also the same thing which I discussed earlier, is the pressure what you're having at the end of the nozzle with respect to the ambient pressure. This ratio will give you the pressure ratio. If the pressure ratio is less than 4, then you go for conversion. If it is more than, you go for conversion and diversion. So you need to calculate the pressure ratio. Once you calculate the Mach number and the pressure ratio, you have to calculate the actual exit velocity. We have a whole formula for the actual exit velocity, which I will discuss at the moment. And here we got the ideal exit velocity, which we can calculate at the standard conditions of temperature and the pressure, which we will do at the testing time. So here, actual exit velocity. For the actual exit velocity, the formula what we are having over here is nothing but the exhaust velocity. What is the velocity of the exhaust gases what you are having at the tip of the nozzle, which will be responsible for getting thrust. So the formula over here for that is square root of TR by M 2 gamma by gamma minus 1 into 1 minus PE by P gamma minus 1 by gamma. We'll see what is the each of the letter over here denotes to. The T is nothing but the absolute temperature of the inlet gases. Whatever the actual temperature what you're having in the inlet gases in the engine, that is the temperature. Where R is a universal gas law of the constant, which is 8.314 kilojoules per Kelvin. Whereas M is a molecular mass of the gases, and gamma is the isentropic expansion factor. It is nothing but the ratio of the Cp by Cv, like specific heat of the gases at the constant pressure to the specific heat of the gases to the constant volume. With that thing of the gases, you can calculate the gamma. Once you've done that, and also you got the PE. PE is nothing but the pressure of the gases, of the exhaust gases at the end of the nozzle. And the P and the P at the denominator is nothing but the ambient pressure what we have around the nozzle. And the same the gamma what we have here is the isentropic expansion factor. So using that you will calculate the exhaust velocity, which is nothing but the exit velocity, actual exit velocity. So once you get that, you can calculate the velocity coefficient, which is nothing but actual velocity with respect to the ideal velocity. So that is how you calculate the velocity coefficient. Once you get this diameter and the velocity coefficient, you can design a basic or a proper line diagram of the nozzle. So once you get that, you have to perform, you have to see the nozzle performance assessment, which is nothing but to check the efficiency. If you are getting the required efficiency with that nozzle, you need to check if you are getting the required thrust with respect to the nozzle. There are formulas to calculate the thrust. There are formulas to calculate the efficiency, which I will discuss now. First one is the thrust coefficient. Thrust coefficient is nothing but like it's the same ratio of the actual thrust what you are getting with respect to the ideal thrust of the aeroplane and the gross thrust, which we'll discuss. Which is gross thrust is also the ratio of the gross thrust at of the exhaust gases at the exit with respect to the ideal. So we'll see what is the formula we require to calculate the thrust actually. So this is the thrust of the rocket nozzle, which is nothing but F is equal to m dot dE plus PE minus PO into AE. We'll see what each letter denotes over here. M dot is nothing but the mass flow rate of the exhaust gases at the end of the nozzle, which is nothing but if we want to see what is the mass of the exhaust gases going outside the nozzle with respect to per second or per minute. And whereas BE is nothing but the exit exhaust velocity at the nozzle, and PE is nothing but the pressure of the exhaust gases at the end of the nozzle, and PO is nothing but the ambient pressure around the nozzle, and A is the cross-sectional area of the exit of the diameter of the nozzle. So once you put all the details, you can calculate the thrust of the rocket nozzle.
What is the area to measure the diameter of the nozzle?
Area to measure the diameter of the nozzle is nothing but the tip of the throat. The tip of the throat diameter what you are having, that will decide what is the aerial cross section of the nozzle. So that is where you are having actual high velocity. So once in the convergent, as you see over here, this is place where you will get the higher velocity. And in the convergent and divergent here, which I will explain later on, which will the lines which will show where the velocity is higher, pressure is less, and the temperature is less. So here you got the thrust of the rocket nozzle. So there are in subsonic and the sonic conditions, especially in the sonic conditions where the pressure ratio is 1, where the pressure what you get, as I discussed in the optimum nozzle, where the pressure you get of the exhaust gases at the end of the nozzle is equal to the ambient pressure of the around the nozzle, where the pressure ratio is equal. In that cases, the thrust of the rocket nozzle is nothing but F is equal to m dot V equivalent, which is nothing but mass flow rate of the exhaust gases at the end of the nozzle with respect to the exit velocity of the exhaust gases at the nozzle. So once you get the thrust, you will know what is the actual thrust you are getting because of that whole exit velocity of the gases outside the nozzle. Thrust is a really important thing. That is the main thing what we require over here for the rocket. So with some design of the nozzle, with some dimensions or with some whole line of the nozzle, you will get the thrust. But the point over here is we need to check if we are having a proper efficiency with that, if we are achieving the real efficiency what we require. To check the efficiency, we need to calculate the specific impulse. To calculate the specific impulse is nothing but the ratio of the gross thrust what you are getting with respect to the mass flow rate of the exhaust gases into the GO, which is nothing but the gravitational acceleration. It's the same thing, like F is a thrust which is going into the opposite direction because of the exhaust gases, and M into GO is nothing but the masses of the mass flow rate of the exhaust gases which is coming out of the nozzle in the downward direction. So it's the same again, the Newton's third law of the motion, which is opposite, each and every action has its equal and opposite reaction. You have to see if you are getting the proper thrust, enough thrust with respect to the exhaust gases what you are getting outside the nozzle. So this will decide if the nozzle what you have designed is giving you a proper efficiency or not. This will give you the value of the specific impulse, which is nothing but the fuel efficiency, because the whole exhaust gases what you are getting is by running the engine, which is nothing but fuel consumption. So you have to see if you are getting the proper thrust, efficiency with fuel efficiency, which is nothing but efficiency of the nozzle and also the fuel efficiency. So this is the brief idea of what we got about how we need to calculate the exit velocity and what is the thrust we are getting in the plane and also the specific impulse. Now this is just a line diagram of the convergent and the divergent. We'll see what exactly the temperature, pressure and a velocity will vary with respect to the nozzles. So when at the end of at the tip of the engine where the exhaust gases will be exhausted, the temperature will be high, the pressure will be high, but the velocity will be low. So, but at the end, at the throat, where you can see over here, you can see the red line is the temperature which is decreasing, the black line over here is the pressure which is decreasing, the temperature, the velocity over here which is increasing. Whereas in the divergent again, the velocity will still increase because of the expansion is constrained, and the temperature will go down and the pressure will go down as the expansion is constrained over here. As the expansion is more with respect to the throttle, the pressure will definitely decrease. So ultimately what you're getting over at the end of the nozzle is higher velocity, less temperature and less pressure. The main parameter about the pressure what nozzle design engineer had to consider over here is they have to minimum the total pressure. Almost they have to make it to zero, or else it has to be equal. It has to be related to the atmospheric pressure, equal to the atmospheric pressure. That is one of the main attributes what a design engineer nozzle has to do. So once the design is done, once nozzle design has been done, it is mandatory for all the aerospace companies to certify their products, certify their components. Now we'll see a certification procedure for an aeronautical component, nozzle and also for the wing. First we'll see for the nozzle. Actually the procedure for the nozzle and the wing will be almost the same. So we'll just go along with that by discussing the nozzle and the wing. Well, certification process is actually certified by several authorities. Here the process is for the Federation Aviation Authority, FAA, who will certify the product with respect to see if the product what the aeronautical company has designed is within their limits, within the safety region, within the margin at which the plane can go and it can experience the conditions when it is in the air. So finally they will give you the airworthiness approval, which is nothing but the certification of the component. So to start with here, I just want to explain a few things. Like this is the convergent nozzle, this is the convergent and divergent nozzle. In the convergent nozzle, we need to see where the nozzle is fixed to. That is fixed to the engine. So for example, if the engine, and here you got the nozzle which you connected, it means there are few actual loads which are being applied at the nozzle, at the inlet of the nozzle. So the red lines what you see over here is the loads which are being applied at the inlet of the nozzle. As this area will be open, there are no any direct loads which are being applied. There are few aerodynamic loads which will be applied, which I will discuss later on the dynamic analysis. And the same way this is in the convergent. So to start with, first the process which I am going to explain is not it's not the process, but for the certification there are much more processes or much more complex procedures which a aviation company follows to get it certified. But what I am here going to discuss is the basic and the most important analysis which a aeronautical company do on their component to get it certified. First one is the structural analysis. This is nothing but load, stresses and the thermal. Load and the stresses, these are very important things in the nozzle, because the nozzle is made to decide the direction of the exhaust gases. That will decide the thrust, the direction of the thrust. If the direction of the thrust changes, the whole back pressure, the whole thrust what the plane is getting will change, which will lead to the imbalance in the plane. So what we have to do is the loads what are being applied, the what are being directly loaded on the nozzle should not affect the nozzle to displace its position or to get deformed, or should not get fractured, which will directly change the direction of the exhaust gases, which will directly change the exit velocity and the thrust vectoring, the change of the thrust is known as thrust vectoring. So that thing should not happen. There are few procedures for thrust vector is a thing which actually the planes use while landing the aeroplanes. Well, at the time of the landing, there is one capability where that it wantedly change the direction of the thrust. That is a different thing, because you want to get the whole plane into control and you want to reduce the friction on the tires of the aeroplane, then use the thrust vectoring. But over here, changing the thrust direction with respect to the damage or because of the deformation of the nozzle is a different thing. So we have to stop that, we have to control that, we have to see if the whole design of the nozzle is within the limit so that it should not get deformed within the actual extreme loads which are being applied on the nozzle. So we have to check that. The other one is there should not be any scratches on the nozzle, there should not be any dents. Even that will change the direction of the exhaust gases, which will lead to the thrust. And the other very most important over here is the thermal analysis. We have to see the thermal coefficient is maintained all over the nozzle. We should see there should not be any thermal expansion, because the temperature which is being maintained at the end of the nozzle is very high. Because of the higher temperature, the nozzle diameter will change. If the nozzle diameter will change, the whole thrust will increase, the whole thrust will decrease with respect to the design of the nozzle. So the diameter should not change, which is the thermal expansion. So you can do all this using in the FEM model, like FEM method. There are many softwares in the FEM which you can do directly the static analysis of this nozzle. So once you've done the static, you'll go for the dynamic analysis. Dynamic analysis is nothing but testing the nozzle in the real time. Testing the nozzle by applying all the possible loads on it. Like whatever the loads and the stresses and thermal what we have over here, we check only with the effect of the loads which are being applied over here and the temperature. Whereas the dynamic analysis, you will check with the mode shifts, you will check with the vibrations, you will check with the damping and the frequencies. Like the engine is fixed to the nozzle, because of the vibrations of the engine, that will affect on the nozzle, because of which the nozzle will vibrate, even that will change the whole thrust. And frequencies, because of the whole velocity or the pressure or the temperature at which the exhaust gas is coming out of the nozzle should not make the nozzle unstable, which will change that as well. And also the damping, it's all because of the vibrations, the whole nozzle will get affected. And the mode shapes is nothing but the change in the shape of the nozzle because of the loads, stresses, thermal, frequencies and everything. When everything comes into attack, the mode shape will come in the imbalanced shape, which is not unique. So that thing will change the thrust, and that will change the whole process as well. So this is the dynamic analysis. To this structural analysis, you apply all these frequencies, damping and all the possible things which will apply on the nozzle, and then you will do the dynamic analysis. So once you've done that, you will go for the aeroelastic analysis. This is the very important analysis over here, because this is the real-time analysis. In this you will do inertial, elastic and aerodynamics. All the three analyses are done together. All the three analysis conditions and considerations are put together, and then the analysis is done. Elastic is nothing but the structural, inertial is nothing but the dynamics, aerodynamics is nothing but the aerodynamics concept, like the effect of the air when the plane is moving with a certain speed. The air which will be cutting the plane will affect on every part of the aeroplane surface with certain pressure. So even you have to consider that into consideration as well. This will be the final test which will actually show you what is the performance of the nozzle with respect to all the conditions which is having it around. So once you're done with that, you'll go for fatigue analysis. Fatigue analysis is a very important analysis which is actually done for each and every component in the aerospace. Because when aeroplane is something which it is in the air, there is no way you can change something, there is no way you can do something. So for each and every component, they definitely do the FNDT analysis, which is nothing but fracture and damage tolerance. So they do that analysis to see for how many cycles the component will be stable. After how many cycles the component has to be replaced. After how many cycles the component will get cracked. After how many cycles the component will get failed. So these testings are done on the nozzle as well to see for how many landings and for how many takeoffs the nozzle will be efficient, the nozzle will be capable. So once you've done that, you'll go for testing for the acoustics as well. Acoustics is nothing but reduction of the noise. This is also one of the most important analysis they do in the design of the nozzle to see there should not be much noise disturbances in the jet engine. So this is the actual general process for the certification process for the nozzle, what they do. So once this is done, this will be certified by the FAA, and the certification will be issued by the FAA to the aeronautical company. The same process is being applied on the wing as well. As I explained, the structural loads, stresses, thermal. The loads, as we know, the loads what we will apply on the wing is the engine weight and also the fuel lines and the fuel usage which will be passing through inside the wings, and the aerofoil frame and the ribs is the self weight of the wing, and also the aerodynamics. So that everything will come into the consideration, and because of the engine there will be vibrations on the wings as well, and the mode shapes of the wings because of the wind and the aerodynamics. So as we see in the aeroplane, the wing goes ups and down. That is within the limit, within the tolerance that is allowed. So that is the thing, the wing is in the safety region. So if that go beyond the limit, there is the chances of having the failure in the wing. So they do all the testing with respect to that. And here you see the sectional, here is a side view. You can see all the loads with the black line is the aerodynamic effects on that, and the red ones is the engine weight. And here you can see the flow of the air on the aerofoil structure of the wing. So this is applied as well, and the aeroelastic analysis is also done on that, inertial, elastic, and the aerodynamics. And the fatigue analysis, which is nothing but FNDT analysis, is also performed on each and every component of the wing. Wing has too many components in that, a rib and the passage of the fuel lines, and then a whole big flange to lift the whole engine. So this everything will be tested for the FNDT analysis, and that will be replaced with respect to its own time and after a number of cycles, and the reduction of the noise. So this is the actual general process for the certification process of the aeronautical components for the nozzle and the wing, which will be certified by the Federation of Aviation Authority. So this has given you a brief idea about the nozzle, function of the nozzle, types of the nozzle, and what is the main attributes required for to design, and what is the main thing which actually affects the nozzle, and what are the main things you need to consider while designing the nozzle, and the certification process of the nozzle and the wing. Thank you.
Which are the methods you will use it for dynamic and aeroelastic analysis?
For the dynamic analysis, there are softwares like you can do it in the answers, or you can do it in the NASTRAN and the pattern for that.
I'm asking for the methods which you are working with.
Modular analysis.
Sorry?
Modular analysis.
Okay. Yeah, for both dynamic and for aeroelastic.
Yeah, for the aeroelastic, to apply it all these three, you will have some advanced softwares which I'm not aware of it. So you'll use that methods to apply the aerodynamics and everything. But for the dynamics, you can do it in the NASTRAN and pattern by applying the possible vibrational analysis and the modular analysis for the frequencies. Thank you.